So yesterday we were working with optimization. Whoopsie. I gotta go quick on that without my fingertip, I guess. So we went through the process and we did a couple basic ones, and I'm recording. So shut it. Alright, we did the box, and we're going to go do this rectangular field. One of the 5 you do in your groups will be similar, but different. So you're going to have to kind of know the process. So you've got right here a river. I'll just kind of, this over here is water. And it doesn't matter what you're fencing in. It's just a very common optimization problem in calculus, is where you're using some fencing and you're trying to either maximize area, or you know the area and you want to minimize the amount of fencing you need to buy. So I'm going to do the maximize the grazing area one, but on your not technically your classwork, I guess I'll call it, it's the minimizing the fencing. So those are the 2 types you get. So it says that there's 500 inches of pipe cleaner fencing, and he's going to fence off a rectangular field that borders a straight river. Right? So we're not going to fence this part in right here. And it says he needs to fence in along the river. He doesn't. So just so you know, there's a typo there. We don't need to put fencing along the river. And it says what dimensions of this field will result in the largest area. So I know my area is length times width. I need to get it a function of one variable. It's a 2-variable equation for length times width, so I have to go put variables on here. Whatever this width is, so is this. You can call them anything you want. I could call it W and W, or it doesn't really matter. But my area is just X times Y. But the process, just in case some people listening to the video who are absent, we need to get that right-hand side down to a single variable using the other information. So you always find what you're trying to maximize or minimize, write it down, it'll have multiple variables in it, and you reduce it to one variable. So this said that he has 500 inches of fencing. So I know that my 2 of my x's, because those are the 2 sides of the rectangle, plus the y has to equal 500. Then you'll solve for one of the variables. Pick the easier one. That makes it easier. So on this one, it's easiest to solve for y. So I would say that my y would be equal to 500 minus twice the x value. So that's always the process. What are you trying to maximize, or equate, or minimize? Then use the other information given to get it down to one variable. So now I'm going to have my area as a function of x. So I like to write it like that. You don't have to though. And mine would be x itself times the y, which is 500 minus 2x. Alright? And so then we need to take the derivative, because functions are maximized or minimized at those critical values or the endpoints, but those don't really make a whole lot of sense. So for most of the problems. Like this. So I'm going to write it as a polynomial. So I'd have my 500x minus twice x squared. Yesterday we talked about you shouldn't really use the product rule if you don't have to. And then, what's the next thing I do? You guys remember? Derivative. Yeah, with respect to that independent variable, I'm going to call it a prime of x. Yesterday I called it dA dx, but I like to mess with notation on you. It's interesting to know what notation they used on the AP test. Probably all of it. Right? Like, I don't know if they did a y double prime, an f double prime, or a second derivative like that, but they expect you to know all of it. And then this would be minus 4x, and we want that derivative to equal 0 so we can find the critical values. So I'm going to write 0 equals. Normally you're challenged with factoring right here, and so I'm going to factor it even though this isn't a quadratic. I'm just going to factor it anyway. I'm going to pull it just so you know that factoring is always the way to go. So I've got that. Looks like my x falls out nicely, as I should put 125 of the 500 units of fencing there, another 125 of the 500 units of fencing here, and then what would this be? 250 on this side. If you were asked what is the maximum area you can make with that 500 units of fencing, you would just multiply these two. So can someone do that for me? I don't have a calculator. I don't have one on my desk real quick. Oh, thank you, Kristen. So whatever 125 times 25 is, I remember from last hour, it's 30,000 something. 31,200 and what? 50 square units of area is what the maximum you can get. And the one you're going to do is going to give you the area restriction and ask you for the minimum amount of fencing. So a little bit of a twist. The next one we're going to do I really like. It's a little bit more complicated. I'm trying to see if I can turn the page here over here. So the next one we're going to do is about somebody out swimming in the ocean. There we go. So here it is. All right, I'm going to draw a nice picture for this one. Tomorrow I think I'm going to change the schedule because there's a super cool problem that goes with this, sort of. It's more complicated, but there's this college mathematics professor. I don't remember the university, but he noticed that his dog, it was a corgi, I think. And his article got published because it was very kind of cool what his statistics or data showed. But he found that when he would throw the ball off the dog would jump off the dock, swim to the ball wherever it was, and always seemed to take the optimal route back to shore. Does that make sense? And he was thinking, does this dog like intuitively know what the optimal route is? So he did this statistical study where he would kind of measure and all this stuff, and it turned out the dog was actually intuitively knowing how far he should swim and then run along the shore to have the optimal choice. It's very weird. And so he got published, and the article, I didn't publish the whole article because it's huge. But the actual problem itself, I did staple in here, and I think we're going to do it tomorrow, and then we'll work on number 5, because last time we didn't get to number 5 of the 5 problems. But it's this dude, here it is. He was Hope College, Holland, Michigan. So you can read it if you want, but he is minimizing his expenditure of energy intuitively. This is doing it with calculus. So what it says is I'm out here in the ocean, so I'm going to go draw the ocean. Oh, that was blue already. Sweet. So here we are. Draw me. I'm out in the ocean. I'm going to use all my artistic skills here. Here I am. Looks like I'm doing the dead man's float. I should have put my arms the other way. So now I'm doing the backstroke. There. I am out there. And I'm 1 mile out, it says. So I'm going to put a 1 mile right on that leg. And I want to get to a town 3 miles down the coast. So I'm going to grab this. Let's go down the coast here. I want to go, here's my town, right here, and it's 3 miles. I need to swim to the shore and then walk along the shore. And this is what that college professor said his dog was actually optimizing his expenditure of energy, which is kind of strange. Would I do that in the summer on my dock and figure it out? No. But it was interesting. And it says, at what point along the shoreline should they stop? So there's some spot, this is the shoreline. There's some place along here. I'm going to put a dot line. Oh, I'm going to the fingertip. No wonder. I'm like, why won't this change colors? All right, let's go right here. Put a dot right there. And let's put an X on this. All right? So it's X that's changing. Like, what spot along the shoreline should we swim to so that the time it takes to get to town is at a minimum? So finish off this right triangle. X is changing, and we want to figure out what it is. Like, where should we swim so that the time it takes me to get to town is at a minimum? You might say, well, just go along the hypotenuse because that's the shortest leg. But I'm swimming slower than I'm walking, correct? So you might say, well, do the least amount of swimming, but then I've got the longest route. Does that make sense? So there's some point along there where I'm going to optimize it. And it's the time that I want to minimize. So write time min. All right. Here's the problem, though. There's nothing on here about time. Don't you agree? Right? I've got some rates, and I've got some distances, but I've got nothing about time. I'm going to write my total time. I'm going to write time subtotal just for a second. I know that it would equal the time I swim plus the time I walk. That's pretty understandable, right, Joel? But again, there's nothing on here about times. I know I'm going to swim this distance. So let's figure that out. What is the distance right here as a function of x? I want you guys to tell me. The 1 squared plus x squared's square root, correct? So Pythagorean theorem, that will give me the distance as a function of x. And this length over here as a function of x would just be 3 minus wherever it's at. I do know the distances I'm swimming as functions of x. Right, Joel? It makes sense, right, Jacob? Right? That makes sense. The distances we've got going as functions of x. I've got the rates, but I still have nothing about the times. So you have to go back to elementary science, and how are those three quantities related? Yeah, so you learn that distance is equal to rate times time, and she just solved it in her head for time. Time is distance over rate, correct? So I'm going to go over here and write my time as a function of x. The thing that's changing on here is x. So the time it takes me to swim will be the distance I'm swimming divided by the speed at which I'm swimming, or the rate. So that's my time I'm swimming for any value of x. And then over here, I'm walking 3 minus x distance, and I'm doing it at a rate of 4. So it's just what Chris has said. It's distance divided by rate to get your time. Now that everything's a function of x, I'm ready to go. Because I want to minimize that time. So what am I going to do with my time function? Take its what? Derivative. Yeah, it's just got a little chain rule in it. So it's not just a easy polynomial, but it certainly isn't a hard derivative. So over here, that's minus 1/4. That's obvious because it just is. On this one, though, you have to chain rule it. So you guys go ahead and chain rule that really quickly. I'll give you a minute, and then I'll hop in and do it. Meanwhile, I'm going to take a bite of my sandwich, so I don't have time to finish it. You're having pencil issues, bud.
No, I don't have pencil. I'm just looking for tissue.
Oh, I don't know.
Okay.
All right, so there's my derivative with the chain rule. And I'll clean it up. I'm going to get rid of these 2's, and I'm going to throw my negative exponent in the bottom, and I like roots. So it looks like I have an x over 2 root 1 plus x squared. Is that what you guys got? Or did I make a mistake? No, I think it looks pretty good, doesn't it? Oh, I did. I did forget it. I just wasn't done. All right, so there. And that's my derivative. It's all, this would be called my dt dx, or my t prime of x, and I want it equal to 0. So it looks like I'm down to having to set this guy, because I can't factor obviously, equal to 1/4. So a lot of old stuff comes into play when you're doing applied calculus, because it's not always just about the calculus. So we had to do a little common sense right here, a little Pythagorean theorem right here, a little basic science up there, and right here, what am I going to need? Real world problems aren't usually about just one math skill, right? So what math am I going to need right here to solve this? From, I'd say, the 8th grade. Crisscross, yeah. I'm just going to multiply and set my cross products equal. So this would be 2 root 1 plus x squared. Done. I'm going to just divide by 2 so I can see it. And now I'm just doing algebra. So the calculus was minimal. I had to know that to optimize, I needed to find those critical values. I had to know how to take a basic derivative, but the rest of this is all common sense and basic math. I'm going to square both sides. And then it looks like my final equation is going to give me 3x squared is equal to 1. Keep going over here. So my x squared would be equal to 1/3, making my x plus or minus, but that doesn't make sense because I'm going forward to get to town, would be 1 over root 3. I like to see a number for that. That'll tell me how many miles in from shore would optimize that route. Okay? And can somebody do 1 divided by, I remember it's 0.5 something from last year. You guys are in their second hour, so you kind of remember some of it. We'll do it on your calculator for me, will ya? Whoever did the last one. Kristen, will you do for me 1 divided by the square root of 3? It's going to be 0.5 something. 7. Thank you. So that's how far we should swim. It's about 6/10 of a mile, and then we should walk 2 point. We should not how far we should swim, but where along the shore we should swim to. And we're done. Looks pretty, and I wrote really neatly. Aren't you proud of me, Krista? That's nice. The next one's all about cat food. All right. I told you yesterday this is used a lot in marketing for packaging. And sometimes the optimal route people won't buy. For example, the optimal way to make this can so that it holds 6 ounces is not generally the type of can a person wants to buy for a cat. Do you get why? Why do you think they're short and round? So the cat can get their little snoot in there, right? We give them this taller can, but this would actually be the process if we wanted to minimize the amount of material we need to use. So we'd save money. But then fewer people are going to buy it. It's all kind of like a marketing issue. But we've got 6 ounces that we want to make sure we're selling or packaging. We've turned that into inches. So that's our volume. It's 14.5 cubic inches. And how should I construct that can so that the material needed to make the can is at a minimum? That's why they charge more, by the way, for those pops that are in the tall glass. Does that look like a pop? That does not look like a pop. Let me get that out of there. Sorry. That did not look good. Anyway. Oh, now I'm going to get the giggles. All right, so those tall glass bottles of pop or beer or anything you buy in the tall bottles cost more, right? Because of the packaging. So let's go take a look at this guy. We want to minimize the surface area. So we need to write a formula for the surface area of a cylinder. I would challenge you to think it out. My geometry class has a test tomorrow on areas and volumes, and they will have to find the surface area and volume of a cylinder. But they have a formula sheet. But you guys should be at the level of math where when you forget a formula, you should be able to think it out. When you cover this can, what's 2 obvious shapes you're going to need to cover? The top and the bottom, yeah. So there's plus 2 pi r squared on it because we need to construct 2 circles. So in the machine shop, to make any can like this, there's 2 circles that are made, correct? And then there's another shape made, a rectangle, that gets folded, correct? So it's kind of like maybe there's a seam in the can right here. In a machine shop, the rectangle gets folded and sealed, and then they seal on 2 circles, right? So I just covered the circles. But that rectangle I need to account for as well. The height of the rectangle would be the height of the can. What would the length of the rectangle be? The circumference of the circle. How do you get circumference of a circle? 2 pi what? R. Interesting that that's the derivative of the area. It's not only interesting, it's not a fluke. There's mathematical reason for that. Like the derivative of the area with respect to r is 2 pi r x the circumference. Pretty cool. Anywho, let's go right then on here. 2 pi r h would be, that's our formula. My geometry kids, they just have it written in front of them. But you guys should be able to think it out. So now I have 2 variables on there, so I can't start my derivative. I need one variable. I need to either have it be a function of the height or a function of the radius. So I'm going to write my secondary equation. They told me the volume was 14.5. How do you get volume of a cylinder? Not because you memorized it, but maybe you get what volume is. You cover face, and then you fill it up with height. Correct? The face of this would be the circle, pi r squared, and then we'll fill it up with the height. So pi r squared each. All right, so in this guy, which one's easier to solve for, r or h? We'll get the same answer either way. One way is just going to be uglier. Which one of these h is easier? Yeah, so choose the easier one because you're the one who has to deal with your choice. So 4.5, oh bless you, over pi r squared. Now I'm going to plug it back in, so I have my surface area as a function of the radius. I like to write it as S of r. And that's going to equal 2 pi r times my h in terms of r, 14.5, over pi r squared. Somebody just walked by and looked at what was on the board. Probably won't get here anyways. All right, here we go. Well, not very many do. 10% of you guys, I think. But I'm not ripping on them. The majority of people don't get they because it's a fact. Right? It's not no, it's factual. There's a difference. What? Oh,
I still find it funny.
Well, thank you. And then now it's recorded too, so super. All right. Didn't even think I forgot about that. I might have to do a clip. All right. They probably won't get to this lesson. But someone was just kind of standing looking and like, what are they doing? All right, anyway, I'm going to cancel my pi's. I'm going to get a 29 over my r, because my r is going to cancel, plus 2 pi r squared is now my primary equation as a function of me changing the radius of the can only. All right, now I can take the derivative. A little bit of an easy power rule going on. Right? So, negative 29 over r squared. Agreed? Because it's just 29r to the negative first. And this is a function of r, so there's no times dr, d anything. I guess it's times dr, dr. But plus 4 pi r. We want that to equal to 0. Whew, this is a lot of work. John? Is it hard work though? Not really. No, just kind of leisurely right now. So I've got this equaling 4 pi r, and then I'll do what Bella said, crisscross. I guess what she wants to call it, so that's what we'll call it. 4 pi r to the third.
Where did you get the r squared on the bottom from?
Taking the derivative of 29r to the negative first. I brought that over. And then I knocked that down to a negative 2, and then I shoved it in the basement. You're welcome. All right, so now I'm going to divide by 4 pi because it's a number. That'll give me r cubed. So I'll cube root it, and then I'll have Kristen and whoever else was using their calculator, because I don't have a concept of the magnitude of that radius without seeing a number. The cube root of 29 over 4 pi is a little too abstract for me, but I'll take it, and that will be the radius that we would make the can. 1.32 inches is what we should make the radius. Its height was a function of the radius, so if I wanted to set the machine to make the can, I would set it for a radius of 1.32, and I'd have it stop pulling on it when its height reached whatever this turns out to be, and I don't really care. You good? I think that might be it. Is that the last one? Right, because did we do the last one yesterday with the girth of the shipping box? Okay, perfect. So I'm going to pause this.